Welcome to The Explainer. Today, we're going to break down a classic coding challenge, but one with a really fun twist. We're talking about traversing a binary tree from the bottom up.
Okay, so here's how we're going to tackle this. First, we'll unpack the challenge itself. Then, I'll show you the tool we're going to use. It's a real workhorse. After that, we'll do a visual walkthrough to see it all in action, check out the code, and finally, wrap it all up with the key things you need to remember.
All right, first things first. Let's really get to the heart of this problem. What does it actually mean to see a tree from the ground up?
Normally we think of a tree traversal as starting at the very top, at the root, and then working our way down branch by branch. But this problem flips that on its head. It wants us to start at the very bottom, with the leaves, and climb our way back up to the root.
So check out this example, right? We get this tree as input. Our job is to spit out a list of lists. But here's the real kicker. That deepest level, the one with nodes 15 and 7, that has to come out first. Then the level above it, and so on, all the way up until the very last thing in our list is the root node 3.
So, how are we going to solve this? Well, the good news is we don't have to reinvent the wheel here. We're going to use a super powerful, tried-and-true algorithm that's pretty much perfect for this job. It's called breadth-first search, or as you'll often see it, BFS.
And honestly, the name kind of gives it away, right? You explore the breadth of each level before you move on. My favorite way to think about it is like exploring a building. You're not going to just run down the stairs. No, you're going to check every single room on your current floor before you even think about going to the next one. That's BFS in a nutshell.
So how does this actually work? Well, it's pretty simple. The key is a data structure called a queue. And you can just think of a queue as a waiting line, like at the grocery store, first in, first out. You start by putting the root in the line. Then you process it, and you tell its children, hey, get in line. And you just keep doing that over and over until you visited every single node.
Okay, theory is great and all, but let's actually see this thing in action. It'll make so much more sense. We're going to walk through our example tree and see exactly what a normal standard top-down BFS gives us.
Okay, so we're starting fresh. Our queue, that waiting line, is empty. And our final result list is also empty. The very first thing we do is add the only node we know about so far, which is the root, node 3, into the queue. All right, time to process level 0. We take 3 from the front of the queue, we add its value to our result list, and then we add its kids, nodes 9 and 20, to the back of the queue. And just like that, level 0 is done. Next up, level 1. We're going to process everything that's currently in our line, which is 9 and 20. We pull them from the front, add them as a new level to our result, then we look for their children. Well, 9 doesn't have any, but 20 has 2, 15 and 7, so they get in line.
And here we are at the last level. We take 15 and 7 out of the queue, add them to our result. Now, do they have any children? Nope, so nothing new gets added to the queue. And because the queue is now empty, boom, our traversal is complete.
Okay, and this is the aha moment. On the left, you see the result we just got from our standard BFS. On the right is the result we actually want. Take a second and look at them. What do you see? They're the exact same levels, just in perfect mirror image reverse order.
So the solution, it's almost laughably simple, right? All we have to do is run a standard BFS, get the result top down, and then just flip it, reverse the whole thing. It's such an elegant and efficient way to solve this because we're not inventing some crazy new algorithm. We're just using a tool we already know and adding one tiny little step at the end.
All right, let's see what this looks like when we actually write the code. And I promise, it's surprisingly straightforward.
So the core of this code is a direct translation of what we just did visually. We set up a BFS loop, we use a queue to go through the tree level by level, and we collect all those levels into a list. Let's call it ANDs. It's literally the exact same logic we just walked through.
And then, here it is, the magic trick. After that whole loop is done and we've got our top-down list, we just return AND's slicing notation. Now, if you're a Python person, you know this little slice notation. It's just a super clean, super Pythonic way of saying, hey, give me this whole list, but backwards. It creates a reversed copy. And that's it. That one little bit gives us the perfect bottom-up order we were looking for.
Okay, so let's wrap this up. What are the most important things you should walk away with? Let's boil it all down. First thing, this solution is efficient. The time complexity is O of n, and all that means is that the time it takes is directly proportional to the number of nodes, n, in the tree. Why? Because we visit each node exactly once. Simple as that. The space complexity is also O of n, mainly because at some point our queue might have to hold all the nodes from the widest part of the tree.
So the core technique here is just beautiful in its simplicity. You just perform a totally standard top-down level order traversal with BFS, you store the levels as you go, and then at the very end, you just reverse the whole list. You know, this is actually a fantastic problem-solving pattern in general. Solve the simple, standard version of a problem first, and then see if a tiny tweak can get you to the finish line.
And that really leaves us with a great final thought, doesn't it? This problem, it seemed tricky at first, maybe even a little hard, because it asked for something unconventional. But the solution? It was just a clever little twist on a standard algorithm we all know and love. It really makes you wonder, right? How many other hard problems out there are just waiting for a simple, elegant solution that's